Wave interference is a fascinating phenomenon that occurs all around us. When two or more waves meet and overlap in space, they interact with each other in specific ways. This interaction between waves is fundamental to understanding many natural phenomena, from the sounds we hear to the colors we see. In this video, we'll explore what happens when waves combine and the different types of interference that can occur. Wave interference happens when two or more waves overlap in the same space at the same time. When this occurs, the waves don't bounce off each other or destroy each other. Instead, they combine to form a new wave pattern. This process follows the principle of superposition, which states that when waves meet, their effects add together. The resulting wave is determined by combining the displacements of all the individual waves at each point in space. The principle of superposition is the key to understanding wave interference. It tells us that when multiple waves pass through the same point, the total displacement at that point equals the sum of the individual wave displacements. This can be expressed mathematically as y total equals y1 plus y2 plus y3, and so on. This means we simply add up the displacement caused by each wave to find the resulting displacement. This principle applies to all types of waves, including sound waves, light waves, and water waves. Constructive interference occurs when two waves meet in phase with each other. This means that the crest of one wave aligns with the crest of another wave, and the trough of one wave aligns with the trough of another. When this happens, the waves reinforce each other. The result is a new wave with a larger amplitude than either of the original waves. Think of it as waves working together to create a stronger effect. This is why sounds can become louder when sound waves constructively interfere, or why light can become brighter. For constructive interference to occur, there's a specific mathematical condition that must be met. The path difference between the two waves must equal a whole number multiple of the wavelength. We express this as delta d equals n times lambda, where delta d is the path difference, lambda is the wavelength, and n can be 0, 1, 2, 3, or any whole number. This means the waves travel distances that differ by exactly one wavelength, two wavelengths, three wavelengths, or no difference at all. When this condition is satisfied, the waves arrive perfectly in phase and reinforce each other. Destructive interference is the opposite of constructive interference. It occurs when two waves meet out of phase with each other. This means the crest of one wave aligns with the trough of another wave. When this happens, the waves cancel each other out, either partially or completely. The result is a wave with a smaller amplitude, or in the case of complete destructive interference, zero amplitude. Instead of reinforcing each other, the waves work against each other. This effect is used in noise-canceling headphones to reduce unwanted sound. Destructive interference also has a specific mathematical condition. The path difference between the two waves must equal an odd multiple of half the wavelength. We write this as delta d equals n plus 1/2 times lambda, where n can be 0, 1, 2, 3, or any whole number. This means the waves travel distances that differ by half a wavelength, 1.5 wavelengths, 2.5 wavelengths, and so on. When this condition is met, the waves arrive perfectly out of phase and cancel each other out. Wave interference has many practical applications in our everyday lives. Noise-canceling headphones use destructive interference by generating sound waves that are out of phase with unwanted noise, effectively canceling it out. Concert halls and auditoriums are carefully designed to promote constructive interference, ensuring that sound waves from the stage combine effectively to reach the audience with maximum clarity and volume. Soap bubbles display beautiful, colorful interference patterns because light waves reflected from the inner and outer surfaces of the bubble film interfere with each other, creating the rainbow of colors we observe. These examples show how wave interference is not just a theoretical concept, but a phenomenon that affects our daily experiences.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.